Welcome back to the shrine. Today on the altar, some fine motor engineering stuff. From all the scattered parts, you can see something's going on. What we're gonna do today is we're gonna try to figure out the profiles of these cams. So these are cams from the cylinder head that I purchased for my project, and this was the first one a couple of years ago. And as you can see, there's a intake, there's an exhaust cam, and so these two are clocked relative to each other, and they also clocked relative to the motor, which if you look on this side, this is where the large gear is mounted. And you can see that the spacing of the threaded holes is not uniform. Okay, they're not spaced 120 degrees, but rather this spacing here is about 100 degrees, and then this spacing is 100 degrees. So that way, the gear can only be assembled one way. So this is the cam, again from the original engine, our cylinder head that I bought. Now I got 6 more of these, since I bought 6 more cylinder heads that I've been trying to measure. So there's 1, 2, 3, 4, there's 2 more here. So what I'm gonna do is put these in the device and measure the profiles of the cams. Now, the way this works in the engine is you have a timing mark up here. So when you put these camshafts into the engine, you adjust this timing mark so it matches the timing mark inside the cylinder head right here. There's also a timing mark down in the engine, and so when all these match, then the engine is properly timed. A couple interesting things that I wanted to mention. The first one is about tolerances. So these screws here that mount the chainring to the camshaft are metric 5 size, and the size of the hex is 9 millimeters. And you can see that I just loosened the screws so they're not even finger tight, and I'm holding the cam steady, and you can see that the gear can rotate about 1 degree. So that's how all these tolerances will stack up basically against you if you are an engine designer. So there's no pin here, and I mean like a ground pinhole with a ground pin, or a spring type pin that would always position the gear relative to the camshaft in a specific position. And you can see that it's got about 1 degree play, and yet it still works. So at the end of the day, the position, the initial position of the cam is going to be off a little bit, but it's still within the bounds that the engine is going to be able to operate at. The other thing I wanted to point out, that this is the first camshaft that I bought, and then years later I bought 6 more of the same part number from the same supplier. As you can see, there are certain differences between them. One of the main differences is basically that this bearing is shifted to the left, and there's an extra cam here. So this one doesn't have that extra cam, and this one has the cam. And the cam basically looks like this. So it's got like a little finger, and it is resting on a one-way clutch relative to the camshaft. So you can turn it in this direction, and you can feel that there is some kind of spread clutch or one-way clutch inside. So it's turning in this direction, but it's not turning in the opposite direction. It will lock up, and it's real fine. So this is like a free wheel in a bicycle wheel, in a rear wheel of the bicycle. So I think what this does, it prevents the chain lash or some kind of dynamic effect. The way it works, it's got a thin plate that it is connected to. So here's this plate, and this plate has a spring-loaded finger on it, and this is coupled to this clutch. So when it's spinning in this direction, it's preventing to backfiring, but it can always spin in this direction freely. So I did not deep dive into the exact working of this, because I'm not going to use this for my purposes, for my engine, but it's quite interesting. If you guys know what this exactly does from dynamic standpoint of view, please put it in the comments. Thank you. So a little bit about this device that I came up with. This is basically a cam scanner, and what I did here is on this rail I mounted a stepper motor, and then on the far side I mounted another stepper motor, but this is missing the rotor. So I'm purely using it just for the bearings, so it's providing me a platform. And both of them are mounted on this right angle bracket, so I can move them in and out in a specific direction. Furthermore, this motor has a spring-loaded center, so I can pull it back like such, and I can put the camshaft in between. Let's see, I need to remember how it goes. So I can put the camshaft like so, and then once I start to spin the stepper motor, it's going to clock the camshaft with a specific rate. So the angular division on the stepper motor is 0.9 degrees. That means that if I tell it to go one step, the rotor is going to turn 0.9 degrees. So if I want to do a full revolution, then I have to go 400 steps. Now what I can do is I can go 2 steps at a time, so 1.8 degrees or 3.6 degrees. But I've done this before, and especially in the region where the cam starts to lift, I need a relative high resolution to figure out that point exactly. So what I'm going to do is I'm going to use 0.9 degree increments, and so I have to go and start and stop it 400 times. So to measure the cam rise, I'm just going to use a digital indicator. This is one of those digital indicators you guys seen I used in the previous video. And so I'm going to remove the tip, and I'm going to add a cam follower tip. Okay, all this is just a little cam follower, and it basically has a little roller, and it's on a spring pin. Okay, and it's a perfect match for the indicator, so this will screw in here, and then I can adjust the angle and tighten up this lock nut so that this cam is parallel to this plane. And what I did here is I created a bracket that matches the end of the indicator, and now I can mount all this on the standoff, and then there's a screw that will hold everything together like so. Okay, so as far as the cam goes, as I mentioned earlier, this camshaft is shorter than that camshaft. So first what I need to do is remove the bearings from this one, because I'm going to use that surface to mount a coupler. So I machined this little coupler which will go to this side, and once I tighten it, it will lock it up. I also have a little plate here that will couple this coupler and this coupler together, and I can still use the end for the cone so that the inside of the shaft hole, you can see there's a chamfer on it, so it's going to rest on this cone and it's going to maintain some concentricity. I ended up using the press, not the hydraulic press channel, but just a simple arbor press, and I remove all these bearings. And the secret to the clutch is revealed. So you can see it's just a simple clutch with 3 clutch pockets. There's 3 rollers, and they are preloaded with little springs so that this one-way clutch runs in one direction and it will lock up in the other direction. I've designed quite numerous of these for starter motors. So this internal section, this internal diameter is ground, it's hardened and ground, and then these pockets are of cylindrical nature. They just offset the center of these pockets, these rolling pockets or surfaces. It is offset relative to the center of this, and that creates a clutch action, so those pins will lock in. So you can see it's real fine. It's not like the freewheel in a bicycle where you have pawls, but this has kind of an infinite locking feature, so it can lock in any position. There's a truss washer that looks like this, and then there's the bearing. We are ready for measurement. As you can see, I moved the driving motor back, and then I moved the idler motor a little bit, and all that was necessary to make sure that this gear, this driving sprocket, lined up with this hole here. You can see that the bar, the maker slide, has a hole in the center right there. So that has an important reason. I made a pin, and this pin is rounded on one end, and it happens to match the space within the gear. Okay, I'm trying to show it this way. So you can see that it matches that space within the gear. So once I insert this pin into the hole, I can find the 0 position of the gear. So basically I'm mimicking the clocking of this mark relative to the housing. So I'm going to start the measurement at that vertical position. As you can see, I assembled the indicator, and I can go and clear the indicator. So now it's at 0 position. And I also hooked up the motor to the controller I made, and it's got this clicker switch here. So when I click the switch, it tells the Arduino to go and move the motor for one division. So you can see that I'm still on a base circle, and when I'm turning this camshaft, then it is showing that number going up and down. So that means that there's a certain amount of runout, which is not really runout but offset. So the center line of the camshaft does not line up with the center line of the motor. This can be due to the way I constrain this on the tapered surfaces or some other reasons, but that's just how it is. I should have done a coupler that mimics this bearing journal where the bearing sits, but I did not go to that length, and also there is a certain amount of tolerance in every operation I do in my workshop, so I just have to live with that. So what you can see here is when I'm turning it, you see right now it's 0, and then I go, let's say 90 degrees, and it goes up to 22 microns. So that's pretty much the actual runout I have to live with. I also need to make sure that the follower, the roller follower, does not fall into the oil gallery holes. So you can see both cams have an oil gallery here, and typically that oil gallery hole is put on the leading surface to the cam, so the cam rotates this way. So if you have a rocker arm, the rocker arm is sliding in this direction, so that the oil is going to be introduced under the rocker arm when it's going up on the cam. You can see that's the story on both sides. So this is the exhaust, and then this is the intake side. Also you can see that the two cams are not the same width. So the intake side is wider and the exhaust is narrower. I didn't notice that until now. So the exhaust is 8.4 millimeters wide, and the intake is 10.4 millimeters wide. So it is wider, and it's due to the fact that when the intake is opening, there's still pressure in the cylinder, and so there's more pressure on this side when the cam is opening the rocker arm. Now if you look at the old one that I initially purchased, you can see that it's the same size. So the exhaust is 10 millimeters and the intake is 10 millimeters. Found the original code from 2019 November. So this is Arduino. You can see there's just a lot of declaration here, a bunch of variables. So you can see that number of divisions for 360 revolution is 400 right now. So I can make that, let's say 10, and then I'm just gonna go and flush this onto the Arduino. Arduino is blinking rapidly. It says uploading, done uploading. So now if I go and I turn on, then it should go 36 degrees. And you can see it's doing 36 degrees. So it is gonna break up a full circle into 10 divisions. So that would be 36 degrees. So I have to push it 10 times and it's gonna do a full revolution. So this gear has 28 tooth. So I can go here and basically change that to 28 and then flash it. So It is uploading. It says done uploading. Okay, we're gonna go and restart. We're gonna go and restart this, and we're gonna go and send it to 1 revolution. So you can see it's 12 degrees. I have no idea what the second number is, but it's always 228. So yeah, I just need to look up this code and I can figure it out. But the point is, the first number is how many degrees it accomplished. So second time 25, 38, 51. And you can see right there on the bottom, relative to that hole, it always goes to 1 teeth. It always accomplishes 1 teeth clocking. So I'm going to go and reset and then restart the measurement. So the pin goes in like this, and then I find the opposite gear space. As you can see that the pin engages that gear. There's a little play, but that's okay. So that's my 0 position. Pull the pin out like that, and then come here and 0 it out. So that's my 0 position. And now I can come here and start the serial monitor. And then once I press the button first time, it is going to turn 1.8 degrees. Okay, and then here I can see what is the lift. It's actually dropped. You can see there's a negative sign here, so it dropped 2 microns relative to that 0 position. Got about 25 points. Takes about a minute to record 25 points. It's really fast. It's all manual, but you can see all these negative numbers. So it starts from -2 microns, goes up to 38 microns, and then it just came down back to 0. So that's the run out of the shaft. That's the coaxiality of the shaft, the camshaft relative to the motor shaft. So I can take that out analytically or manually or algebraically, I guess. The intake side is completed. You can see the cam profile here. That's the orange one. The exhaust is next, and you can see that I started at -002, and that's in millimeters. And if I go to the last number here, it shows -016. So started at 2 microns negative, finished at 16 microns negative. So that's 14 microns off. I think that's reasonable. And now the important thing is to see if this gear came back to that 0 position. And you can see the mark down there. And I can put the pin in, and you can see that it came back exactly to the same position. So it went a full 360 degrees, which is great. That's what we want. So now I can reposition the indicator to the exhaust, and then start over, and then do the same thing with the exhaust side. The exhaust side is completed. It came back to 2 microns, as you can see right here. If I go up all the way to the top, you can see we started with 0, so it was 2 microns off when I came back to the 0 position. This is how the cams look relative to each other, Again, the orange is the intake, and then the blue is the exhaust. And I started at this location here, so at the top position, that's where I started scanning, and it's going clockwise. The scan is going clockwise. And drum beat. But if I take the pin, and again I insert the pin here, it should engage the gear perfectly, and it does engage the gear perfectly. So that scan was a success. I don't think I'm gonna do all 6 of these, so that was number 1, and then there's 5 more. I'll probably do 1 or 2. It takes about 10-15 minutes to scan one entire side, and then you get that result. So I'm gonna go and scan a couple more, and then just overlay the data and see how much difference there is between them. Also, you can see the serial report here. So we got back to 359.9996. This is because I'm using just some stupid variables in my Arduino code, so it doesn't go back to exact number. Honestly, you can tell at this point that, yeah, this is a CDI indicator. There's a connector here, so I can basically get a cable hook up to this connection point on the indicator and then tie it to the Arduino, and the Arduino can directly read this, so I can set up a manual code where the Arduino is switching the motor with a given step rate, and then it knows the angle and it's reading the indicator and basically does this whole thing manually. The problem is it takes a lot of programming, a lot of troubleshooting, and I just have to balance between you know, how much time I spend on tool development and how much time I actually use that tool. Actually, this cable that interfaces with the CDI, I think it's like $260 just for the cable. I do have a print for the cable and the pinout. I know how to connect it to the Arduino. Again, it takes time and effort, so I decided to do this manually, and so far it worked. I finished scanning the 3 different camshafts. So I scanned number 1, number 2, and then I scanned number 5 right here. So I'm going to take it out, and what I'm going to do next is try to measure the base circle radius and the maximum cam rise. So this just comes out like that. It's that easy. Okay, so it's number 5. So I have the micrometer here set up, and you can see that it's completely wound in. And now I'm gonna go and open it. I already set 2 millimeters. So we are looking around 20 millimeters, I guess. So I'm measuring 3 different positions, and what I do is I try to clock the camshaft 5 degrees, maybe 10 degrees to the left, 10 degrees to the right, and then the middle position. So 21,053. This is number 2 intake cam. 21,069. 21053. Let's look at the exhaust cam. 21065. 21085. 21080. So I updated the numbers both for the intake and for the exhaust right there, and it didn't change the results much. I can use the back arrow, and you can see that was the original camshaft that I scanned previously, and this is the new one. So there's 0.2 of a millimeter difference between the base circles. So this is the chart for the intake and exhaust. Well, you can't blame me for not trying. I tried to insert the cam like so, and then try to find that cam rise, but it's a futile try. It's really hard to find where is that maximum point, and I'm holding it in my hand, so it's real hard to position. So I think this is highly non-repeatable. So I'm just gonna discard that step and basically trust what the cam scanner told me. So the problem is that the cam scanner doesn't know what the base circle radius is. So that's what I measured with the 1 to 2 inch, and I'm gonna include that in my Excel spreadsheet, and then it will properly provide me with the cam profile. Here's a comparison of the scans. Red, blue, and green curves are the current camshafts, while the yellow is the old one. As you can see, the blue and the red curves are pretty close to each other, while the green right here, number 5, is slightly clogged relative to the red and blue. I'll probably use data from the number 1 and number 2 curves, which are the red and the blue. This is the exhaust cam, and this is the intake cam. Down here are some plots for cam rise as a function of angular rotation. Again, there are compound errors from the fixturing, initial position, and some other measurement errors. I just have to live with these. Thanks for tuning in today. I hope you enjoyed the video, or maybe learned something. If you like it, please give me a thumbs up, and if you like the channel, please subscribe. See you next time. Bye.